Okay, chapter 7 then. First thing in chapter 7 from the basic section is if you've ever got a polynomial over another polynomial, the first thing you need to do is to check that they factorise. If they factorise them and look for any common factors to cancel. This will simplify everything before you even start. If they don't factorise, then we'll come on next year 13 what to do in that situation in order to write them in a different way. You might have already started it actually, it's the stuff to do with partial fractions. That's when they don't factorise. But next thing is the factor theorem. The factor theorem simply states that if f of x is divisible by x minus 1 or x minus a, then f of a is equal to 0 and vice versa. So if you're ever asked to show that something is divisible by a factor like x minus 1, substitute in 1 and show that it equals 0 and properly show that it equals 0. So here I would write 1 plus 3 minus 5 plus 1 equals 0. So actually show that rather than kind of skipping that. In show that questions, it's important to show every step. You can't skip steps. There's a few kind of easy things to do with proof and then some more complicated stuff to do with proof. Easier things are proof by exhaustion. So if you're given a finite set of values to prove something is true for, just substitute each of those in. You can't do that, say, with all the natural numbers or all the positive integers because there's an infinite amount. But if you're given like 7, you can just substitute each of those 7 numbers in, show that it's true for all of them. So normally there's some kind of algebra, you substitute it in and you show that the statement is true. If you want to show that something is not true, the easiest thing to do is just find one example where it's not true and write that down. So that's called proof by counterexample, and it's for disproving a statement. In the intermediate section, we've got polynomial division. So polynomial division very often follows the factor theorem. So you're asked to use the factor theorem to show that something is divisible by something, and then the next step is divide it. So in this case, I've done this one divided by x minus 1. The things which point that people tend to make the mistakes on most is the subtraction step. So a lot of people are okay with doing their x cubed divided by x, that's x squared, multiply it back out, and then this step is where people tend to make the mistake. 3 take away minus 1 is 4. So you very often see things like 2 written there, and then everything goes wrong after that. You can tell that things go wrong afterwards, and I'll show you in a second. Same thing with the next bit. So you do, I've got 4x squared, so divide that by x, and you get 4x, multiply it back out, multiply the 4x by minus 1 and by x, and then take it away. Again, this commonly makes a mistake. Minus 5 minus minus 4 is minus 1. And then finally, put a minus 1, times it out. If this doesn't come out to be 0, and you've already proved that it is divisible, you've made a mistake. Okay, this should come out to be 0 for every one where you've already proved that it is divisible. So go back and check. Specifically check the subtractions are done right. Following that, sometimes the question ends, sometimes it will ask you to factorise something completely. So for this one, this will be the factorised version. It's just, that's one of the factors, that's the other factor. If the quadratic factorises further, do that as well. This one doesn't, that's it. It's got surds as the other two solutions. If you're asked to find all the roots, you've already got one of them, which is x equals 1. The other ones are for when the quadratic is equal to 0. So just solve that using the calculator. If something asks you to show that a cubic has only one real root, like it has to have at least one because it goes from minus infinity to positive infinity, so it's got to go through the x-axis. But you've already found one of the roots by doing the polynomial division. Necessarily you've found a root. In this case it's x equals 1. If this quadratic has no real solutions, no real roots, then the one that you've already found is that one. This does have other solutions, they're surds, but if that didn't have any solutions because the discriminant was less than 0, then you just have one real solution and two imaginary ones. The last thing is the proof. Proof is awkward because proof could be anything from all of maths. It's hard to pin down exactly what a proof question could be about, but in year 12 especially, there's a few things that they ask repeatedly. These are some of them, so if you get lucky you might just get asked to prove something by exhaustion or by counterexample. And then the last one is often they ask you to prove some algebraic thing. Normally it's proving that something is divisible by something. They'll give you some algebra like n cubed plus 2. Prove that that is always, never divisible by 8. So all you would do is, and it always says this, for all positive integers, or n is a member of the natural numbers. So the natural numbers is the same as the positive integers. It's 1, 2, 3, 4, up to infinity. So in that situation, you can just split into the even numbers, which is 2 times n. If it says n in this part, you'd use k or something else. Not n, because that was in the original question, just literally any other letter. So 2k for the even numbers, substitute that into the algebraic thing that's in the question, and then show that it's not divisible by 8 or whatever the question says. And then do the same thing for all the odd numbers. Because if you've shown it's true for all of the even numbers, and you've shown it's true for all of the odd numbers, that's all of the positive integers done, and you can complete your proof there. There are other things that you can do. I've seen questions where it's split into 3, so multiples of 3, 1 more than multiples of 3, 2 more than multiples of 3, which is similar to this. This splits it into 2 because it's evens. It's about the 2 times table, so it's 2 times a number and 1 more than 2 times a number, so that's all the numbers. But you can do that with 3, you can do that with 4. The latest year 13 test had it split into 5, so it was 5 multiples of 5, 1 more than multiples of 5, 2 more than multiples of 5, 3 more than multiples of 5, and 4 more than multiples of 5. That's awkward, but that is all the numbers. It's every number is either a multiple of 5, 1 more, 2 more, 3 more, or 4 more. And when I say all the numbers, I mean all the positive integers, not like halves and stuff like that. So that is about it. And yeah, that's it for chapter 7. Thanks.